session we are going to discuss about fluid transportation processes and specifically focusing on the motive device used for liquid transportation, that is pump. So you see that to go for the basics of, before going to the basics of this pump functioning and the governing equation of pump, we'll first discuss about the classification of pumps. So you see that pumps are majorly classified into two broad groups. So pumps, these are motive device used for liquid transport, right? And here the primary division is this non-mechanical and mechanical pumps. So you see this non-mechanical pumps, they are devoid of rotating or reciprocating parts, whereas mechanical pumps, they essentially contain that, okay, and that actually mediates the power transport of a power transport from the motor to that fluid, right, in this mechanical pump, this rotating accessory or this reciprocating accessory. Now non-mechanical pumps, the major examples are acetate, airlift pump, and steam jet ejector. So first we will discuss about these three in brief, which are not given, these three descriptions are not given in the handout because of its very elementary structure. But the steam jet ejector, we have a separate section in the handout of heat transfer, and we will discuss that later. So what is acetate? See, this device was quite popular in transporting corrosive fluid like acid in chemical process industries long back, right? What's that? It's a horizontal tank partially filled with liquid to be transported, right? We have the delivery line inserted deep towards the base. We have a supply line that is fitted with a check valve, that's non-return valve, right, such that there is no backflow. So this is the delivery line. Here we have the supply line. Definitely we will have a drain, and this this is the check valve. Here we have the drain. We have pressure indicator. We have vent loaded with a safety valve, and a line for the delivery of compressed inert gas. Right? That's the basic structure of acetate. So you see what will happen. Once we have the liquid here, which will be pressurized by this inert gas, so definitely the liquid will flow through this delivery line. Okay. So it's a very, very elementary design, but was highly useful in older days chemical industry, maybe 50, 60 years back, right? Because for the transportation of this corrosive and hazardous liquid, nowadays we have even centrifugal pumps with anti-corrosive linings, or also we have these readily available diaphragm pumps used for transportation of corrosive liquid. But these are also costly, right? But still today in small process industry we still use this arrangement, the non-mechanical pump, which is devoid, as you can see, it's devoid of any moving or reciprocating part for the transportation of corrosive liquid like acid. Second, airlift pump. Here, this is the reservoir from which the liquid to be pumped, and what we insert? We insert a large diameter pipe. Let's say this is the direction, with an expansion at the bottom, right? And here we charge compressed air through a sparger system or distributor system. So here we are charging compressed air, and the liquid to be pumped is filling the reservoir or sump tank. What will happen? Here we will have the vigorous generation of the bubbles, and these bubbles will entrain the liquid towards the delivery. Right? It will basically entrain the liquid. How it will entrain? Because whenever a bubble moves through a pool of liquid, a compressed air bubble, it will assume a shape like this, and individually it transport this much amount of fluid, right? Shape of the bubble of compressed air through a column or through a pool of liquid. Right. So these bubbles individually are entraining a definite amount of liquid. So if my bubble density, a sparging rate of this bubble through this distribution system is pretty high, we can transport an appreciable amount of fluid or liquid through this delivery line. So this is delivery, this is the inlet or this feed tank, right? So that's called the airlift pump. Airlift pumps, this airlifting technique has also been used in biological reactor, where the microorganisms are to be circulated, otherwise they will lose their potency and the cell death will happen. So that's called airlift reactor. You see that this airlift reactor looks like this. There is a side loop, and here we have this air sparging system, right? So what will happen in this arm, the liquid will be lifted and it will fall back to this arm, right? So there is a continuous circulation of liquid being maintained by this air. And why we cannot use mechanical pumps? Because whenever this microorganism, say if I am feeding a pump here, the microorganism, whenever it passes through these impellers or the piston, right, it will be strained and the shell may tear apart. So in order to have a non-sheared mechanical system, right? Non-mechanical system where we don't have any motive accessory like rotating or reciprocating accessory, then the cell will be intact and it will maintain their regular functioning. So to have this, to implement this specific condition, we circulate the broth in this fermenter through this airlifting mechanism. So this is the use of airlift pump, right? Next is the steam jet ejector. We will discuss it in detail in heat transfer, particularly when we will be discussing this evaporator section. But here for this particular section of pump, we will have a very basic idea of the steam jet ejector. Now, steam jet ejector actually consists of highly converging nozzle, right? A set of parallel nozzle, which are inserted in a box. And this box is connected to the device. Actually, this is a device used to produce vacuum, right? So here we have a device where we want vacuum. This is a process device, right? So in the steam jet ejector, after this box, we have a converging diverging section. And it goes to this condenser section. We will not discuss it. So it's going to the condenser section. Now through this nozzle, we deliver medium pressure MP steam. Right? So as we are delivering high pressure steam, what will happen? In this region, its velocity will be heavily increased and the pressure will be reducing. So here in this region, a vacuum will be created. Right? So as the vacuum is being created, what will happen? The material from this process device will be sucked in because of inevitable pressure gradient. So it will mix with this steam, and the mixing is further facilitated by this converging diverging section, and it will flow to this condenser unit. And here, as we are using this water as a component, we can directly, instead of indirect contact heat exchangers or condensers, we can use direct contact condenser, and finally it goes to something called barometric well, the condensate going to the barometric well. We'll discuss the detail. I'm not going into this basic, this detailed design of this steam jet ejector, but here, because here our perspective is pumping. So you see that whenever we create a vacuum, the material is being sucked in. So this is typically a pumping action, right? And the vacuum is to be sealed. So basically here we have a steam jet ejector. Here, see, okay, let's have a discussion. Here we have this direct contact condenser, right? Where water is being sprayed. Right? And here we will have the condensate. So the condensate is released in a tank at the ground called the hot well, right? Which seals the vacuum. Okay? And this trail pipe, the long trail pipe, is called barometric leg. And its height will be 34 feet. Why? Because here we have atmospheric pressure. So against this absolute vacuum, we know that water column can rise up to 34 feet. So this barometric leg, if it is 34 feet high, so definitely there will be no back mixing. Now from here, we are having this non-condensable, which we may feed to another steam jet ejector and from there directly to the hot well. So there may be multiple series of the steam jet ejector and these direct contact condensers in sequence based on the degree of vacuum or the amount of vacuum we require here in the process device. So these are the three non-mechanical pumps. Now coming back to the mechanical pumps, we have to understand that there are again majorly two classifications. One is the dynamic pump, another is the positive displacement pump. So I am erasing this part in order to further extend this tree diagram. So you see this dynamic pumps. In this dynamic pump, we majorly use the centrifugal force produced by the rotating device, right? And that's why centrifugal pump be the primary element in this specific group or member of this specific group called dynamic pump. So this is mechanical pump. So in mechanical pump we have two major classifications. One is the dynamic pump and another is the positive displacement pump. Now in the dynamic pump we have members like the most prominent one is centrifugal pump. Next we have turbine pump, we have propeller pump, we have jet pumps. Centrifugal pump, there are also a lot of classification. It may be single stage, multi-stage, it may be single suction, or alternatively double suction. We can have different classification of the impellers as well, that is closed impeller, open impeller and semi-open impeller. Closed impeller, open impeller, semi-open impeller. We can further have classifications like the curvature, based on the curvature of the impeller. We will discuss it in detail. That is backward curved, it may be forward curved, or it may be radial. Right? Whereas this reciprocating pump, you see, positive displacement pump, there are primarily four classifications: piston, plunger, or rather, here first we will have the reciprocating pump. The positive displacement mechanism can also be implemented in rotary action, though the action is typically different from centrifugal pump. We will discuss it. So this is rotary pump. So reciprocating pump has got further classification like piston, plunger and diaphragm. Whereas rotary pump, there are classifications like based on the rotating elements, we can have gear as rotating element, we can have screw, we can have vane, we can have cam, we can have lobe. Though the basic mode of action remains the same, but these are the different elements based on which we call them as gear pump or vane pump or cam pump, etc. All are the principle of action based on this rotary positive displacement. Here it is piston, plunger and diaphragm, it is the reciprocating positive displacement mechanism. So you see this in most of the cases of process industry in liquid transportation, we use centrifugal pumps, right? Because of its high flexibility, standard, easy design and definitely of low cost. Except we mostly will try to use the centrifugal pump except some specific cases. Majorly, see, we use centrifugal pump except these cases. What are the cases? If viscosity is greater than 1000 centipoise, 1000 times greater than water. If this high head and low capacity that is a volume flow rate is required. And 3, if the dissolved gas is greater than 5% volume to volume. Right? So this will create some problem here. We'll discuss this, why the dissolved gas, if it is percentage is pretty high, like above and over 5%, then what is the problem going to happen? We will discuss that once we understand the functioning and the operating principles of centrifugal pump. Right? On the other hand, see, we are majorly discussing this centrifugal pump. Right? Now, piston, plunger, etc., we are not going to discuss. Basically, these covered in standard semester courses, and basically we don't have question in GATE. Just for a very basic understanding, I am giving you an idea that piston pumps, we will use it where the pressure requirement is above 500 atmosphere. Plunger is extreme pressure greater than maybe 1000 atmosphere. And diaphragm, it operates to 200 to 300 atmosphere for corrosive liquid. Diaphragm pumps are made for corrosive liquid. Whereas rotary positive displacement pump, they are used for clean viscous liquid, for pumping clean viscous liquid like lube oil. The lubricating oil we can transport by using this rotary positive displacement pump. Correct? Now, piston pumps, just have a very basic overview that the piston pump, what are the components? See, or rather, let's put it in this side. These are the extreme positions of the piston. This is called IDC, inner dead center, and outer dead center. Right? Here we have the connection of the pipe, which is always fitted with the check valve. Right? So here we have the reservoir. And again, the delivery line is also fitted with a check valve or a non-return valve. Right? So it's going to this delivery port. Now this piston is connected to a rod, and then we have a mechanical device called crank, and this is called crankshaft. This is crankshaft, this is the crank, this is connecting rod, this is the piston, here we have the cylinder, supply line, this is supply check valve, delivery line, and this is the delivery check valve. See, this crank and crankshaft mechanism actually transforms this rotational motion into periodic motion and vice versa, right? So the crankshaft is just like this. Now see, if it rotates in clockwise or anti-clockwise, whatever it is, the direction, what will happen? This crank will move like this, a radial arm, and when the crank is in this position, or rather this is the connecting pin, right, which connects the crank to the connecting rod. This is pin joint. So when the pin is at position 1, the piston is at IDC, and whereas the pin is at position 2, the piston will be at ODC, right? So this mechanism, which actually transforms this rotational motion into periodic or oscillatory motion, is typically used in automobiles, because in automobiles this power is being generated through these IC engines here in this form of piston. The piston then reciprocates, and that is being converted into this rotational motion through this again crankshaft arrangement. Right? Here it is just the reverse. Here the power source is the crankshaft, and that power is delivered to the piston for its reciprocation. So you see that the piston reciprocates. Now the piston, when it is moving from IDC, initially let's say the position is at IDC. Now if the piston is moving towards ODC, definitely a vacuum will be created and the liquid will be sucked in. Right? So the liquid volume will increase and the piston, up to the piston, moves to the point 2. Next, this is the suction stroke where we are not having any delivery. So in the reverse direction, when it moves backward, what will happen? Now it cannot flow in this direction, we have a check valve, right? So it promotes the flow only in this direction. Here it promotes the flow only in the outward direction, right? So what will happen? The liquid will be, the pressurized liquid will flow through the delivery line and it will be going to this discharge point. So this is typically the action of piston pump. Now what is a plunger? And there is, I would like to mention that in piston pump, if I plot the volume flow rate versus T, it will be just like a half-wave rectifier type plot in a single piston pump. Because over this suction stroke, there is no flow, only over the delivery stroke, the discharge stroke, we will have the flow. Now this intermittent zero flow we can change actually if I go for double acting piston pumps. This is single acting piston pump, and what is the double acting? Where liquid is admitted on both sides of this piston. See, a double acting piston pump, this is what I have described. It's the single acting piston pump. We can have also this double acting piston pump. Which simply it's like this. I'm not drawing the detail. Here say the piston, here it is the connecting rod, right? So we have a common suction line branching into two compartments and also a common discharge line branching out from these two compartments. Okay? So this is the suction and this is the discharge. What will happen now? When the left cylinder, or the say this part 1 and part 2. So the cylinder part 1, when it is undergoing suction, cylinder 2 is undergoing discharge, right? And vice versa. So as a consequence, we can have a full wave rectifier type plot of flow rate, what we obtain at the outlet of the pump. It will be like this. Okay. Now further, if I want to minimize, then we will go for parallel single acting cylinders. Like 3-4 pumps, they are connected, or 3-4 cylinders rather, they are connected in parallel, right? So that is the parallel cylinder, And actually that is the real life example of centrifugal piston pump, or this reciprocating piston pump, parallel cylinder pumps. So if there are only 2 cylinders, it's called duplex pump. If there are 3 cylinders, it's a triplex pumps and all. So here what will happen? We have attached these cylinders parallelly, right, like this, and there will be some common shaft. This is the common crankshaft, but it has got some vanes and all in order to maintain this standard phase difference. So this is the crankshaft here, right. So on this crankshaft, actually these are cranks. This shaft is straight. So this is a symbolic representation. These are the cranks, and cranks are placed like what I am talking about. If this is the crankshaft, one crank is placed like this, another crank may be placed here like this, and another crank may be like this. And these are individually connected to 3 cylinders. So such that they are having a phase difference of 180 degree covering up this entire circle of 360 degree. Now what will happen here? Like the first, this is second, and this is third. And everyone will be having a phase difference of 120 degree. See, this is the contribution of the first. This may be the contribution of the second. And this may be the contribution of the third. Right? So overall, we will have a nearly constant flow rate like this. So it is simply the superimposition of the individual graph. So you see that if I connect this suction like here, and like here, there is a common suction, and similarly there is some common discharge. I am not showing it in detail like this. So common discharge, individually they are fitted with these check pumps. So that's the multiple parallel cylinder this reciprocating pump. Now what is plunger? Plunger is made for extreme high pressure delivery with a very low flow rate. It's a kind of dosing pump. Let's say you are operating a reactor which is at a very high pressure, and you have to continuously feed something or some reactant continuously, but in small amount into that reactor. So there we can use this plunger pump. In plunger pump, see, whenever you have a connecting rod and you are enlarging the cross section into this piston, the piston's area is much larger than the connecting rod area. So if the connecting rod is applying a force F, the respective pressure at this downstream of this piston will be what? Force divided by area. Now if you don't divide it, if you don't enlarge this connecting rod itself connecting rod is functioning as your piston, then what will happen? You can generate tremendously high pressure. So plunger is something where we have the bore itself. It's a thick walled cylinder, and there the plunger simply, plunger means here the piston rod simply reciprocates. And here we have this suction line and this delivery line. Right? So this arrangement must be extremely leak proof Otherwise, as it is operating at a very high pressure, so there are every chances that you will have leakage. Okay. Now diaphragm is same as that of this reciprocating piston pump, but here the edges of these diaphragms are fixed, right? Edges of this diaphragm are fixed. Like what we are talking about, that if I have a groove like this, and here also a groove, in this groove I will fix a diaphragm, and on this side it is connected to the piston rod. Okay, and here you see we have the suction line and we have the delivery line, both fitted with the check valve. Now just like it's fixed at groove, so what will happen if this is the diaphragm? Whenever it is operating in the discharge suction stroke, it will be assuming a shape like this. It will be convex backward line here, and whenever it is discharging, its shape will be like this, right? So it will just move like this. Okay, so there will be a extreme concave shape, and in the next instant there will be an extreme convex shape. And here, why we are using this? This diaphragm is made of metallic or plastic material. This metal, definitely it is to be lined with anti-corrosive lining, right? Or if it is a polymeric material, corrosion, there will be no chances of corrosion. So what will happen? With this diaphragm pump, we can pump corrosive liquid. Otherwise, if you see that is the piston pump, the piston, which is the costly part of this pump itself, it's getting a direct contact with a corrosive liquid. So over a regular short interval, you have to go on changing the piston and the respective accessories, which you don't have to do here, right? Because the diaphragm material is corrosion resistant. So diaphragm pumps are used for pumping corrosive fluids. Okay, so that's about the basic idea of positive displacement pump. So these are totally qualitative, right? So we don't have any quantitative scope right now. Definitely there are quantitative analysis of these piston pumps and these parallel and these double acting pumps, but we are not going into the details of that. We will focus on centrifugal pumps. So you see that the centrifugal pump, let me draw a diagram, and from there we will try to understand the basic functioning of the centrifugal pump initially, and once the functioning is clear, this operating principle is clear, next we will try to calculate the head developed by the centrifugal pump and how it is related to the different pump parameters, and rather the operating parameters like operating speed and the geometric parameters like different dimensions of that. Now you see that in a centrifugal pump we have a shaft, right? Then the shaft is connected to a rotating part of this pump called impeller. Right? So there will be pump casing, but here we have the bearing. Right? And here we will have the inlet, right? And there are some spiral part of the casing. We will discuss it in this once we draw the front view. This is a spiral part of the casing. In sectional view it looks like this. and that's the inlet line. Here we will have the delivery line. Right. So you see, this is the shaft which is connected to the motor. That's the bearing. So what are the parts? This is shaft. This is the bearing. Here we have the sealing arrangement. These are the mechanical seals. This is the central part of this pump, centrifugal pump, which we call as impeller. That is the inlet or inflow. This is suction pipe or suction port rather. This region is called the eye of the impeller. Right? And the spiral part is called the volute, where this is the discharge. Right? So that's the side view of centrifugal pump. Now if I look from the front, it looks like this. Right? Here we have the impeller. Must be a perfectly circular one. Okay, more or less it's this. This is the eye region, and here we have the veins of the impeller. Okay. So you see that here what will happen? This region we refer as impeller tip. This is the impeller eye. These are the impeller veins. this final part of the casing is the volume, and that's the outflow, right? And this is typically the pump casing. Now in general, in this typical hydraulic diagram, here maybe we are having this suction reservoir. We have dipped the pipe, and there we have a valve. I will discuss it, what is the special requirement, and here this is the symbolic representation of centrifugal. Here we have a non-return valve at the end of suction pipe, and that is called foot valve, right? So that's the overall diagram. Now you see that before we start the motor, we have to ensure that here maybe we have a valve, here also we may have a valve, right? A control valve, like all this. So we have to ensure that entire pump casing, right? Entire pump casing and the suction line is filled with liquid to be pumped. Why it is necessary? Because when the impeller rotates, right? When the impeller rotates, this will definitely create a head. Now you see, this head is delta H, and that depends, we will see and we will establish later that depends as some constant, say K, into N square into dA square. So N is the RPM of impeller, and this dA is the impeller diameter, right? So it's independent. The head developed by a centrifugal pump, we can see that it is independent of the fluid properties. Now the point is, the pressure developed is rho fluid into head developed. Now think that the pump has developed a certain head, and a part of it is being used to lift the water through this suction pipe. Okay. Now if I do not fill this line with water, what will happen? The pressure developed, delta P, will be pretty low because it is filled with air, and air has got a density 1000 times lower than that of water. We are supposed to pump water, but we haven't filled this suction line with water. And the pump is developing a head which is only dependent on the RPM and the diameter of the impeller, right? So under this condition, a part of the head developed by the pump will be used, or it is distributed, a part towards this discharge, which will increase the pressure, and the part towards this suction, because it has to lift it, right? So this head, in this dedicated for the suction line, see, that multiplied by the density of the fluid which is filling up this space must be equal to that pressure drop. Pressure drop from here to here, that is to be created. Now if I do not fill it with water, say we are pumping water, but there is air in the suction line. So air density is 1000 times lower, so the pressure drop from here to here will not be enough to lift the water, right? So that's why what we have to do, we have to fill up, we have to ensure that the entire pump casing, this suction line and the part of the delivery line up to delivery valve is fitted with liquid to be pumped, right? And this operation of filling up the pump casing with the liquid is called priming, okay? And if we have air locked in the casing, there will be no lift of water specifically in the suction line, and that is called the problem of air binding. So we have to note here that filling of pump casing, this is a volume, So wheeling of pump casing and suction pipe, this operation is called priming of pump, right? Otherwise, we will have problem of air binding, right? We will have the problem of air binding and no delivery of liquid may result, right? Because we are not lifting the liquid, so definitely we will not get any supply of the liquid at this delivery point. So that's the typical idea of priming and air binding, right? Now you see that why we are using the foot valve? Because for common household pump or very standard pumps, once the pump is shut off, the motor is shut off, you are no longer operating the pump, what will happen? The liquid, whatever was there in this suction line, will drain out. And when you are starting the pump next time, then again you have to fill up with liquid, which is not possible for standard household pumps and small pumps in process industry. So if at the time of installation, if I attach a foot valve at the end of this suction line, what will happen? Then once we are primed, the liquid will always be there and we can start the pump anytime without priming. But for large industrial pump where we may be transporting a liquid which serially formed deposition, like tar we are pumping or like crude oil we are pumping, then if you keep the crude oil within the pump casing or tar within the pump casing, it will deposit and clog, right? So that's why it is to be continuously primed. And for priming large pumps, there are different strategies. We can use an inbuilt steam jet ejector in the pump casing. Like when we are trying to start the pump, first we will operate or first we will then feed this ejector with steam, and that will create vacuum inside the pump casing and will draw the liquid from the suction reservoir. Or alternatively, a small pump may be used to prime the larger pumps. Okay, used for this long distance transportation of maybe crude oil or many other viscous products. Okay, so that's priming, necessity of foot valve and the problem of air binding. Next, coming back to the operation of the CF pump, the primary part of the centrifugal pump is the impeller, right? So when the impeller, you see this impeller what I have used here, it's a backward curved impeller, right? Where the direction of rotation is this, clockwise. So with respect to the direction, it is curved, the vanes are curved backward. So you see this backward curved impeller in open this 3D, it looks like this. This is a single vane, okay, and here we have the shaft. So there may be another vane like this, maybe another vane here, and here another vane. So we have this sort of structure. These are the typical vanes. And here we have the shaft. Right? And very nice representation. So when these vanes rotates, this impeller entirely rotates as it is connected to the shaft. And the standard speed of this shaft, you see, and the impeller is around 700 rpm. So at this high speed, and we have filled up the entire pump casing with liquid, what will happen now? Here we have the liquid, the impeller starts rotating at a very high speed. So the liquid will diverge out towards the impeller tip, which is guided by the vanes, and that's because of the centrifugal force. So governing mode of this transport is basically the centrifugal force, and that's why we refer this pump as centrifugal pump. Now, if we consider three different points, you see, next we have to understand that what is the utility of this spiral part of the casing. Now this region close to this eye, this region, the central region is called the eye of the impeller. This is the tip and this is the outlet. Now what happens as the liquid is diverging out because of the centrifugal force from the region of the impeller eye to the impeller tip, majorly its velocity will increase. The pressure will remain close to each other. The pressure increase is not that appreciable, right? So what you can say that V1 is close to V2 is much greater than V1 and P2 is close to P1, right? So you have increased the velocity through this primary delivery of energy in the form of centrifugal force field to the liquid, and as the liquid moves from this impeller eye region to the tip region, its velocity head will be increased tremendously. Definitely there will be some change of the pressure head, but that is not very significant, right? But think of a pump. Between the inlet and outlet, what we want? We want pressure, right? Pressure rise, severe pressure rise. With velocity head more or less remaining the same, the velocity head is not the desirable form of energy what we want in pump. So the next target will be from here at the impeller tip, we should do something such that this increased velocity head is equivalently converted to pressure head without much loss of energy. And that is being done through transporting this liquid through a continuously and progressively enlarging this channel pathway. Like, if you think that how the fluid moves from this point, rather these points are equivalent to point 2. See, let's think of a streamline moving like this. Now, from this point, because this gap is pretty small, so there will be no leakage in this direction. So let's say this is point A and this is point B, right? This is a single streamline followed by the fluid from different points on the impeller tip to this outlet. Now what will happen? This B, or rather its stream, right? Or this point is equivalent to 2 basically, because these are all impeller tips, right? So you see that along the streamline coordinate S, the streamline coordinate we have discussed it in Euler equation. So along the streamline coordinate S, if you see this channel, you see this cross-sectional area is continuously increasing, but it is gradual increase, right? It's a gradual increase. So dA ds is positive from continuity. We are considering incompressible liquid flow. dV ds is negative, the velocity decreases, and dP ds will be positive according to Bernoulli's equation. So in this volute, the velocity head is progressively being converted into pressure head, right? Into pressure head. However, the increase of this area should be very gradual, otherwise we will have inevitable boundary layer separation, formations of wakes and eddies where the part of that energy will be lost. So the design of volute must be very integrate. It is actually integrate, but nowadays it has been standardized heavily, right? So this volute should be designed and it is to be tested. So like you don't have any baseline design, then it is quite difficult. There will be a lot of trial and error to actually determine that what should be the turn in that volute such that the area increases in such a way leading to no boundary layer separation, and it will be giving you the effective conversion of the velocity head at point 2 to pressure head at this pump outlet, right? So that's about the functioning. So what is being done? first we have to ensure that we will fill up this entire pump casing, suction line and the part of the delivery line up to delivery valve with the liquid to be pumped, because if we don't do that, if we keep it filled with air, the air may not be lifted, right? The liquid may not be lifted from this reservoir, not air, the liquid will not be lifted from this reservoir. There will be not enough pressure driving force we can apply between this point and the pump inlet. Why? Because the pump head is independent of the fluid property and the developed pressure is simply the density into this head dedicated for this suction lift. So as a consequence, if I have air locked in, we may not be having any delivery of liquid at this pump outlet. So for common household pump, we have to prime it at the point of installation, and we will ensure the liquid to be present in the suction line and the pump casing by just inserting a non-return valve at this pump end or the delivery line's end, right? And in larger pumps, we have to progressively prime the pump prior to its startup. Okay? And what are the parts? Parts are that here it should be a leak-proof seal, bearing, mechanical seal, and which is connected to the pump casing. This is a rotating part connected to the impeller. This impeller looks like this. Okay? This is called open impeller. We will discuss it. So this is the impeller. Here it's entirely filled up. Now the impeller starts with a high speed. So fluid, as it is filling up this space, will diverge out towards the impeller tip, acquiring high velocity head or high kinetic energy as it moves from this eye to the tip. Now from this tip, this increased velocity head, which is the primary mode of energy supply, is to be converted equivalently to pressure head as the liquid moves to the point 3, which is the pump outlet. So that is facilitated by increasing cross-sectional area spiral part of this pump casing, and that's called volute. So volute is not actually facilitating the energy transport, but it converts one form of energy, that is the kinetic energy, into another head, that is the pressure head, which is desirable or which actually we want in any pump operation. So in the next session we will discuss about the different types of this impeller, backward curved, forward curved, radial, as well as open, semi-open and closed, and finally we will go for discussing the Euler turbo machine equation, which will relate this head to this speed and diameter and many other similar properties.